So stoichiometry is where we use mole ratios to be able to do calculations to get quantitative information out of chemical equations. And there's a few different terms that you'll see on the IB exam. So you probably won't need to define them, but you'll need to be able to understand them to answer the questions properly. So the theoretical yield is the amount of product that you should make in theory based on a given starting amount of reactants. So the theoretical yield is what you will be able to calculate based on the given amount of starting materials. It's a little bit different than the experimental yield or the actual yield, which is how much product you actually make in a chemical reaction. This is not something that you can calculate. This is something that you have to measure directly in the lab, or that on an IB question, you would be given the experimental or actual yield. The percentage yield or the percent yield is the actual yield divided by the theoretical yield times 100%. The theoretical yield is essentially perfect if every atom were to do exactly what it's supposed to do in theory. So this amount is perfect, and usually the actual yield is less than 100% due to the reaction being incomplete or maybe some different side reactions happening that we're not predicting or thinking about theoretically happening. It is possible to get values over 100%, but that's usually because of impurities or that water's been absorbed or an incomplete decomposition reaction, something like that. But normally we would see percent yields below 100%. Last two, the limiting reactant and the excess reactant. The limiting reactant is the reactant that limits the amount of product you make because it runs out first. So the theoretical yield is always based upon the amount of limiting reactant that you have. It's very important to note that the limiting reactant is not always the reactant that you have less mass of or that you have fewer moles of. Based on the mole ratio, you might have less moles of something, but because you use less of it in a given reaction, mole to mole anyways by the ratio, you may run out of something else first. And the excess reactant is the reactant that you do not run out of, that you will have leftover reactant of, and occasionally you get asked to calculate how much excess reactant is left over. So the key to doing stoichiometry is doing mole ratio questions. There'll be other conversions involved, but the mole ratio is really the key of it. And when you look at a chemical equation, you have to understand that the numbers, the coefficients, the 2, the 1, and the 2 in this example, where hydrogen and oxygen react to make water, those are just ratios. Those are not the only amounts that you can use to make water. You don't only have to react 2 molecules of water with 2 molecules of hydrogen with 1 molecule of oxygen to make 2 molecules of water. Obviously, you could do that any multiple of ways. So you could do 4 with 2 to make 4. You could do 20 with 10 to make 20. And you can do 2 moles with 1 mole to make 2 moles. So the only thing that holds true is that you have to follow this recipe, this ratio, that 2 hydrogens will react with every 1 oxygen, and that combination will make 2 water molecules. So the coefficients always give us the mole ratios, and there's a number of mole ratios within a given chemical equation, depending on how many reactants and products there are. There are different ways to use mole ratios and calculations. I find the simplest way that I've stumbled upon over the years is to simply take the coefficients and set them up across from one another across an equal sign. So I'll try to explain using this example. If you start with 5 moles of oxygen, how many moles of water will you produce? Well, a lot of people could look at this and say, well, it's 1 to 2, so 5 makes 10. We're going to keep the ratio the same. And obviously that will be the answer, but this is a little bit simpler than a lot of the ones, really any of the ones you would see on the IB exam. So just as a matter of practice, here's how I would do it. I would take the coefficients from the equation, which are for oxygen 1 and for water 2, and I would put them on the bottom of a fraction. So 1 mole oxygen for every 2 moles water. So I'm sort of setting up a ratio here without actually making the colon to show it's a ratio. And then on top, I plug in whichever mole amount I actually know. So in this problem, I was given the moles of oxygen. So I'm going to put the moles of oxygen on top of the coefficient of oxygen in the equation. So 5 moles oxygen on top of the 1 mole oxygen. And on the other side, I'm just going to put X. If you want to use N, because that's sort of our symbol for moles, that's also fine. But people sometimes like to use X because they're used to solving for that in algebra questions. So in the end, if 1 mole oxygen makes 2 moles water, then 5 moles must make 10 moles. And so you can see it as the ratio, or if you had to solve it, if the numbers were trickier, in order to solve for x or n as I've now written it, you've got to multiply both sides by 2 to get rid of the moles of water on the bottom. And so in the end, the 2 moles water will cancel on this side, and we'll get 2 times 5 is 10, divided by 1 is still 10, and so the moles of water will be 10 moles of water. So 5 moles of oxygen is enough to make 10 moles of water. That's how you use a mole ratio. You can use them with any equation, and you can use them between any two reactants, or a reactant and a product, or between two products. It doesn't matter how you want to use them. So just do a couple more examples just to show you how they work. How many moles of ammonia, which is NH3, are made when you use up 12 moles of hydrogen? Okay, so the first thing I'm going to do is say there's 3 hydrogens, and I'm going to use the marker, so I'm not going to write in moles H2 just for the sake of time and messiness, but it's probably a good idea to label at the very least that this is 3H2 you're talking about. And on this side, I have 2 for ammonia. Ammonia is NH3. So I'm going to put those underneath my fractions, and then on top I'm going to put the amount that I was given. So I was told 12 moles of hydrogen. Well, the 3 is for the hydrogen, so I'm going to put 12 here. I'm going to put my equal sign, and I'm going to put my x over here. So that's what I'm solving for. So the ratio is 3 to 2. Now you might be able to figure that out, that it's going to then be 12 to 8, but you don't have to if you're not seeing that ratio. You can, again, just solve for x. Multiply both sides by 2. And you'll end up doing 2/3 of 12 is whatever x is, and so x must equal 8. So if you start with 12 moles of hydrogen, that's enough to make 8 moles of ammonia. Again, label things with, at least with formulas, and preferably with moles and formulas to keep everything organized. This is just the quick overview with the marker here. Okay. You can do this for nitrogen and ammonia. That's another reactant product example. So let's do one that's different. How many moles of nitrogen do you need to completely react with 0.3 moles of hydrogen? So again, now this one is with hydrogen, 3 moles hydrogen, but it's also with nitrogen. So the coefficient for hydrogen is 3, the coefficient for nitrogen is 1. So I'm going to come down to my example and write 3 for hydrogen and 1 for nitrogen. Then I'm going to plug in on top the actual amount I was given, which in this case was once again hydrogen. It's 0.3, and so what's x? Well, to get rid of 1, you don't really have to do anything, and 0.3 divided by 3 is 0.1. So x must be 0.1. If you start with 0.3 moles of hydrogen, you would need 0.1 moles of nitrogen to react with that. So the mole ratio step actually becomes quite simple if you follow those steps. Again, I said there are other ways to do it. You don't have to do it this way. This is what I just feel like is kind of a foolproof way. People are comfortable doing cross-multiplying and solving for x, so this tends to work quite well for them. Now we bring in the concept of the limiting reactant. Limiting reactant questions, they will give you amounts of 2 different reactants, and you have to figure out which one is going to run out first. And that might sound tricky at first, but I find the best way to do it, because normally the question doesn't end by just asking you what is the limiting reactant. Normally, if you look down past that part of the question, it will ask you about how much product you make. So I find the best way to do these questions, the way that will kill 2 birds with 1 stone and usually answer the next question on the way, is to see just how much product can I make with each reactant amount. And then whichever one makes less product, that's my limiting reactant. So let me show you what I mean by that. They've started me with 6 moles of hydrogen and 0.06 moles of hydrogen, 0.025 moles of nitrogen. And I want to know what the limiting reactant is. So I'm going to first go up and say, okay, the ratio of hydrogen, coefficient of hydrogen is 3, and that of ammonia is 2. So for the hydrogen one, I'm going to have a 3 to 2 ratio. I've got 0.06 moles, and I want to know how much will that make. So again, I can solve for x, multiply both sides by 2, and I'm going to get that there's enough hydrogen to make 0.04 moles of ammonia. Okay, great. but I don't know if that's the amount that matters. So I have to check the other amount too. So I also know that I have 0.025 moles of nitrogen. So I go back up to my equation and I see that nitrogen is got a 1 in front of it and ammonia has a 2 in front of it. So now I'm going to come down. I'm going to do the same thing, but with that coefficient, or that mole ratio. So this ratio is 1 to 2. So 0.025. And here's my moles of ammonia. So it has to follow the 1 to 2 ratio. So this is enough nitrogen to make 0.05 moles of ammonia. So how much do I actually make? I have enough nitrogen to make 0.05, and I have enough hydrogen to make 0.04. Well, the answer is that I'm going to make this much. Once I've made this much ammonia, I will have run out of hydrogen, and so it doesn't matter that I have enough nitrogen to make more than that. Once the hydrogen is run out, I can't make any more ammonia. So the limiting reactant is not 0.04 moles of ammonia. The limiting reactant is hydrogen. So the limiting reactant is simply the identity of one of the reactants. So it always has to be one of the reactants. And so in this case, because hydrogen allows us to produce less product, that makes hydrogen the thing that limits us. So it is the limiting reactant. And nitrogen is the excess reactant because there's going to be some nitrogen left over. So now in part B, when it says how many moles of ammonia are produced, the reason why I like to do it the way that I just did above is that I've already answered that question. That was the way I figured out my limiting reactant question. So there are definitely other ways to figure out what the limiting reactant is, other ratios you can check, but because this one usually answers the next question for me. So this is the theoretical yield of ammonia. It's the amount of ammonia I can make based on the limiting reactant, which was the hydrogen. The final question, which is sometimes the trickiest one, is how many moles of excess reactant are left over? So now what you've got to do is you've got to take the amount that you actually made, so that's what this is. This is the theoretical yield, how much you made based on the limiting reactant, and you've got to apply the mole ratio backwards to the excess reactant to find out how much you actually used. So I'm going to use this ratio again. It's going to be the ratio between ammonia and nitrogen. It's that 1 to 2 ratio. So I know that 2 ammonias came from 1 nitrogen. But now the thing that I know is how much I actually made. So I know that I made 0.04. And so the question is, how much did I actually use? Well, if you solve for x here, you'd get that x is 0.02 moles of nitrogen. Now that's not how much is left over. This is how much actually got used. You're working backwards from the amount of product you actually made to figure out how much must have been used. So I've used 0.02. If I go back to the beginning, I started with 0.025, and therefore I've got 0.005 moles left over of actual excess. So that's how much of the nitrogen would be left over when I make 0.04 moles of ammonia. So this is the answer to the third question. A couple extra extensions. One, we've talked in the past about Avogados Law. Avogados Law basically says that equal volumes of gas contain equal numbers of particles of gas. In other words, they contain the same number of moles. So one thing that's nice about that is that if you have a chemical reaction that's all in the gas phase, so when you have a mole ratio, like in the Haber process here, nitrogen plus hydrogen making ammonia, 1 mole of nitrogen reacts with 3 moles of hydrogen to make 2 moles of ammonia. That also implies that that's how the reactants would also compare in terms of their volume, because 1 mole takes up 1/3 of the volume as 3 moles, and it takes up half the volume as 2 moles. So what I'm saying is that the mole ratio is also a volume ratio. 1 dm cubed of nitrogen will react with 3 dm cubes of hydrogen to make 2 dm cubed of ammonia. So you can also apply it to any volume, just like we could apply it to any mole amount. This is the volume of 1 mole of a gas, 22.7 dm cubed at STP. So 3 moles takes up 68.1 dm cubed, and 2 moles takes up 45.4 dm cubed. So if you did this at STP, then these are the volumes that each of the individual gases would take up, and they would be in proportion with the mole ratio. So occasionally you'll get questions on the IB exam. It seems to be especially common on paper 1, where they give you amounts, and the amounts are always in dm cubed or cm cubed. And instead of having to actually do any PV equals nRT conversions, you can just treat these almost like they're mole amounts. Like if they said 1.2 moles nitrogen and 6.6 moles hydrogen, you would solve the question in the exact same way. You're just going to apply the mole ratio, because the mole ratio is also a volume ratio. The last extension of the stoichiometry questions is that we don't really have instruments that can measure moles directly. We always convert into moles. So for solids, we convert into moles from masses, which we can measure on a balance. For solutions, we convert into moles with N equals CV, where a concentration is known ahead of time, and we can measure the volume of solution that we use, and then we know how much the moles of solute are in our solution. And for gases, usually we'd probably look at the mass or the volume of the gas to know how many moles we have. So normally in these questions, you don't start, as I did on these practice ones, with moles of reactants and asked for moles of product. Usually you're going to start off with grams of a reactant or the volume and concentration of a reactant. And so all that does is it adds a conversion before you can use the mole ratio. So before I can apply that 2 moles reacts with 1 mole to make 2 moles, I first have to get any gram amounts into moles. So I simply divide the mass by the molar mass. Now I've got moles, and now I can use the mole ratio like I did earlier in the video. If I'm given concentration and volume, N equals CV, I multiply them together, I get the moles, then I can apply the mole ratio. It's also common that at the end of the question, you convert the final amount, like the theoretical yield, into grams or into a volume or a concentration, depending on what the question asks. So we've got lots of practice examples to try, but that's how you use mole ratios in chemical equations.